really need. So 4 quick principles. If you have to deal with these kind of systems, if you're building the system out, what do you keep in mind when you're doing this to make your security assertions sane? Encrypt by default, prefer SSL with client authentication, infer your keys from context, and scope your policy with your artifacts. So why do you encrypt by default? I'll quote Ian Grigg again, who I quoted in a less flattering light earlier, but to remove the weakness of the policy decision. Encryption's pretty cheap, and it's getting cheaper. Processor speeds are still increasing. SSL accelerators are widely available. If you're worried about setting up a web service endpoint, encrypt it. Put it over SSL by default. It's easier to scale that back later when you find you have performance problems than to figure out that you've been getting owned all along and try and do damage correction. Prefer SSL with client off. Again, quick, easy, mutual authentication right at the beginning of the transaction. Inferring keys from context. This is going to be more interesting and relevant after you've seen the whole rest of the talk. But basically, resolving a key is anonymous attack surface. If you have to go out and fetch a key from somewhere over the network, if you have to parse a big complicated message to try and find a key in it, that's a great way for someone to attack you, and that is always anonymous because you can't know anything about someone until you have a key resolved. So if you have a small set of people, if you have a small set of trusted partners, or if you have an application context where you can resolve the key from that context, that's the way to go. And scoping policy with artifacts. This goes back to our tale of two services and the idea that building policy is the same as building a protocol. So if you're writing policy, they should be very simple statements and say things like, every single service that is authenticated with SAML artifact X has to apply encryption and integrity. And if you want to create another set of services that don't require encryption, for example, create a different artifact, create a different authentication point, create a different token that you can use to authenticate people to. And so one question I had when I gave an earlier version of this talk was, so why is this being built? Why are people building web service security? What is it? What's the point? And it really does, I think, enable some strategic opportunities. So my point is not entirely to badmouth it. My point is just to say, don't necessarily drink the Kool-Aid about take all of your systems that you have working today with SSL and switch them to web service security because it's the new thing. What web service security gives you is some strategic opportunities about doing new things with security constructs, doing new ways of doing business. Single sign-on is a great example of that right now. This is something that you can't do very well without these kind of standardized durable assertions. And now things like Liberty, things like SAML, Web Services Federation, are becoming very mainstream. They're changing the way we do business. Card space is another one that's going to change the way we do business. These are game-changing strategies. These are not drop-in replacements for existing technologies. Multi-party distributed transactions, marketplaces, currency-like systems. These are another place where you have some big strategic opportunities out of these technologies. And having some extra expressivity here can create new businesses. But if your business is not creating new protocols, creating new ways of doing business, you should be very skeptical about these technologies. One of the areas I'm excited about is once these do have a chance to mature, once you have these kind of technologies, standard stacks available on every desktop in the world, on every application server, and they're interoperable, there's some good chance that there's a lot of great kind of undiscovered crypto lurking out there from some of the digital cash companies in the early 90s that were a bit ahead of their time and never found their niche in standards. Maybe some of this will have a chance to come back and kind of rework how we do business on the internet. We'll see, but there's a lot more security research needed. So I'll take up to, say, 5 or 10 minutes of questions here if anyone has them on this first part of the talk. Yes?
My way of looking at it, you've got 2 different problems, data at rest and data in motion.
Mm-hmm.
Now, TLS is a great solution to securing data in motion, but lousy for securing data at rest. And now, properly implemented, WS security will allow you to secure the data at rest. And you only want to encrypt the data that you're actually concerned about the privacy. That's data that should not be indexable, should not be searchable, such as social security card, credit card number, information that is truly private. So this should never be a one or the other solution, that you use the WS security only when you have a need to secure data at rest, and that you use
Yeah, so the question or comment was distinguishing between data in motion and data at rest, and SSL being the solution for encrypting data in motion, and WSecurity being a solution for encrypting only pieces of data at rest that you need to have not searchable, that you need to have strong at-rest protections for. And yeah, that's an appropriate use of this technology. And I do agree with you on that. Unfortunately, what I've been seeing and what I've been hearing about in people's deployment is that they apply this to every message. They put their entire database out this way, and that doesn't meet a lot of the needs of organizations and the way they're really using data. People are encrypting all of their data at rest because of PCI requirements, because of worries about data breaches. But the reason they're keeping that data in the first place, you would like to say that that Social Security numbers shouldn't be searchable, but I think the reality of how most businesses work is they do need to be able to search these. They do need to be able to index these. They're building complicated relational databases and using this as a primary key all over the place. Maybe that's not best practice, but
It's also legal.
yeah, well, but I would say that most real-world organizations do want to search and index on their data.
Just like most real-world organizations don't do client off. The entire point behind this was that SSL is great when it's client off. When it's not client off, it's so easy to attack, it's trivial. And there have been tools out there to do so, such as Doug Song's DSNF, that have been out there for 8 years, where you can attack an SSL transport without knowledge of any party that it's been attacked, decrypted, recrypted, and retransmitted. So SSL, as implemented by businesses, is a piece of junk. And providing an extra layer of security around the data that needs to be private is not a bad thing. And going forth and pushing SSL without recognizing that, as implemented, is a piece of junk is a problematic thing to say. I think it's great that you've been pushing client-side certificates, but if you ask everybody in this room to raise their hand whose companies are using client-side certificates, you'll get maybe 7 to 10 people.
That's an issue. The issue was what's the real-world penetration of client-side certificates? And again, I think most people that are using SSL are using SSL for web service, or for websites right now and browser-based stuff. For web services, if you're using SSL, you probably are likely using client-side certs. And SSL, even without mutual auth, can provide strong assertions. I'm going to have to disagree with you on that, and we can talk about it afterwards. I'm going to move on now so we can get to the rest of the material today. Thanks. So the next part is going to be technical deep dive. Go straight into XML digital signatures, take them apart, look at how they work, and look at how to attack them. So why did I choose to attack XML digital signatures? I didn't actually start out looking at it. I'm not a cryptographer, and when I was first encountering systems using this, I kind of thought it was just another signature with angle brackets. It's just XML. And I was seeing a lot of new applications, a lot of new platforms being built on web services, and I wasn't seeing a lot of security testing tools. What I really wanted was something that worked like WebScarab or Fiddler, something that was an intercepting proxy where I could attack and play with these protocols and these applications that do use web service security. And so the first order of business in building a tool like that is to be able to crack open and fix signatures after you've modified the data so you can send along and have it be accepted by the receiving application. And so I started building this tool, and I was running it through its paces, doing interop testing, and I found this signature when I opened up the interoperability test suite. And it's going to take a while to go by here. This is one signature signing about 50 bytes of content. Keeps going. One signature. Oh, missed one there, but yeah. I had to break it onto 4 slides to keep from breaking PowerPoint. So it's pretty ridiculous, right? I looked at that, and
that's no moon. It's a space station.
It's too big to be a space station.
Very bad feeling about this.
So I had a very bad feeling about that signature. And didn't look like a signature with angle brackets to me. It looked like a full-on application cryptographic protocol. And that's kind of something I know how to analyze and break, even if I'm not a cryptographer. Problem here is generality leads to complexity, leads to vulnerability. They've tried to make these systems very general, and in the process, there's enough complexity there that there's a fair amount of space for misuse by developers and by clients, and a fair chance that not everybody got all of that stuff right when they were implementing it. And so I went looking to see what kind of attacks and what kind of research had been done against this, and I really couldn't find much. I found some academic papers on it, but absolutely nothing sort of in BugTrack in the traditional non-academic security world. The academic papers are really good. I would recommend you go check them out. But a lot of them tend to start with sentences like, assume that participating computers and the user's browser B are correct. And I'm surprised that didn't get more chuckles from a room full of security people. Because we have what the architect designed, which here is a formally correct model for putting burning logs right in the middle of your house quite safely, and it's beautiful. Nothing wrong with that design. But when we in the security business go around and kind of crawl in the basement of software and look at how it's built, we often find stuff that looks like that instead. So I decided to go in and deep dive, take a look, pull apart that signature and see what was going on. Followed a basic attack surface analysis methodology. Start with a threat model, figure out what are the entry points, interfaces, what are the operations it supports, what's at what trust level, anonymous, authenticated, authorized, what's remotely accessible, what's locally accessible, things like that. Look for complex inputs. So again, here's this slide with all of the different possibilities, or one of the many different possibilities for web service security. And again, as I said, there's a lot of attack surface there. The goals of the digital signature in this context of that kind of operational model there is to be able to sign arbitrary content, not just XML, but to specifically for XML be able to sign an info set, sign kind of the semantic intent and not the actual byte stream of the message, to have agility in your cryptographic algorithms and key formats, to be able to have flexibility in how you reference material being signed, to supply key info in line if you want, and to specifically allow portions of a message to be excluded from being signed. And this is really great if you're building a really full-blown application stack that you want to be a general-purpose tool that can handle everything. But it makes some really counterintuitive properties for those of us who are used to thinking about integrity and signatures. There's a lot of stuff there that can change without invalidating a signature, and that creates some pitfalls and some tricky and dangerous stuff. So tried a couple different ways of presenting this material, and I think the best way is just walk through a typical signature piece by piece and look at how each piece works and see what the attacks are against each piece. So we'll start with just the basic, how does an XML digital signature work? So we'll start out with our content to sign. Here we have some XML content and some arbitrary binary content. You take a hash of those pieces of content, and now we're going to start actually building our signature. So we're going to take those hashes and create a bunch of XML metadata and store those hashes in our XML metadata. Then we're going to describe in that metadata what are we talking about, what did we just sign, what do these hashes refer to. We're going to take a hash of the metadata, take our key, and then we're going to sign the hash of the metadata. So it's an indirected signature. The metadata is kind of a manifest of what's being signed and what the hashes are,